So this video will cover Argand diagrams and the modulus of complex numbers. So there's two different topics within it. We're going to start with Argand diagrams. This might sound like a new thing, but it's actually something you've got lots of practice with already. And we're just applying it to a slightly new context. So an Argand diagram is basically just a graph. Now we've all seen one of these before. The graph has two axes, an x-axis and a y-axis. The only difference for an Argand diagram is that we're going to get rid of our x and y axis. Now, where we used to have an x and y axis, we're instead going to rename them the real axis and the imaginary axis, like this. Now, sometimes you will see the real axis just being called RE. Obviously, that stands for real. And the imaginary axis being called IM. Obviously, again, standing for imaginary. So now that we've established our real axis and our imaginary axis, we can try filling in some complex numbers onto our Argand diagram. So our first example will be 3 minus 2i. So on the real axis, it's going to be 3, and on the imaginary axis, it's going to be minus 2. So we know that 3 is the real part of this complex number, and minus 2 is the imaginary part. So we'll go to 3 on the real axis. And we'll draw a line down from there. And then we'll go to minus 2 on the imaginary axis. We can draw a line across from here. So this will give us our point here. 3 minus 2. Again, if we link this up to the real axis, we can see this point is 3 on the real axis. We can see the point is minus 2 on the imaginary axis here. So I'm going to give you another point now, and you can tell me where this would be. So the complex number I'm going to give you will be minus 4 plus 5i. So you can pause the video now, try and identify where that will be on the Argand diagram, and press play when you're ready. Okay, so we're minus 4 plus 5i. To plot this, we're going to go to the real axis first of all, and go back 4. So minus 4 is here. Okay, we'll draw a line from there up, because we know the next number is going to be positive. So then we go to our imaginary axis, and the imaginary part of this number is plus 5. So we're going to go to plus 5 on the imaginary axis. We'll draw a line out from there to meet our part on the real axis. So this number meets up with minus 4 on the real axis and plus 5 on the imaginary axis. So it's going to be drawn here on the Argand diagram. Finally, I'm going to draw a point, and I want you to tell me what complex number the point represents. So drawing the point here, we can call this C. I want you to tell me what complex number that point C represents. And you can pause the video now, and when you're ready for the answer, just press play. So our point C, if we try and figure out what the coordinates are, we need to find out its real component. So we'll bring it up to the real axis. We also need to find out its imaginary component, so we'll bring it over to the imaginary axis. So on the real axis, its value is minus 5. And on the imaginary axis, its value is also minus 5, coincidentally. So when we write out the number, the real part is going to be minus 5. And the imaginary part is also going to be minus 5. So it'll be minus 5, which is the real part, and minus 5i, the imaginary part. So we can say that's the value of C. So now that we understand Argand diagrams, it's a good time to have a look at the concept of a modulus. Now the modulus is just a way of comparing complex numbers. Because they're so different to us, and we're not used to seeing numbers in this form that have a real and imaginary part, it can be useful to just think of them in terms of their modulus when comparing them in terms of their size. So a modulus really just means, on this Argand diagram, how far away from the origin, from the 0, 0 point are they? So if we draw a line connecting all of these to the origin, we can probably make a guess at which one is furthest away from the origin. So it looks to me like C is furthest away from the origin, so we could say that has the biggest modulus. It also looks like this point here, and we can call that A, is the closest to the origin. So we could say that this point A has the smallest modulus of the three numbers. And then B, of course, would be somewhere in the middle, so its modulus would be quite big, but not as big as C's. Now, looking at the diagram is a good way to kind of eyeball and estimate which is the biggest or smallest modulus. Sometimes you will be asked to use it that way, but there's also a formula that we can use to calculate a value for the modulus. So we get out a number. Obviously, A would have the smallest number for the modulus, B would be bigger, then C would be the biggest. So we'll look at that formula now. So if we have a complex number and it's in the form A plus B I, we're asked to find the modulus. The modulus will normally be written by putting a symbol that looks like this on either side of the complex number. They look like little bookmarks, they're just lines. So that means the modulus. So to find the modulus of A plus BI, what we're going to do is get the square root of A squared, the real part of the number, plus square root of B squared, the imaginary part of the number. So here's an example of a question now. If the number Z is equal to 3 minus 6i, then find the modulus of Z. So this is our complex number, and we need to find its modulus. To find the modulus, we know we need to get the square root of the real part squared plus the imaginary part squared. So we'll do that now. The modulus of Z is equal to the square root of 3 squared, which is the real part, plus the imaginary part squared. Now it's important to make sure that any signs that are in here, if it's a negative, that we also bring that down. If it was a positive, we wouldn't have to worry so much. But we're squaring this whole number, so we're squaring its sign too. Okay, so if we square 3, we're going to get 9. And if we square minus 6, well, it's going to be 6 times 6, which is 36. And a minus times a minus, which will give us plus 36. Remember, any number that's negative, when you square it, it becomes positive. So we're looking for the square root of 9 plus 36. Now plus plus, we can just say gives us a plus. So 9 plus 36 is 45. So we can say that the modulus of Z is equal to the square root of 45. Now, if this was a number that could be simplified, say for example if it was a square root of 36 or a 49, then we'd of course simplify that. But because we can't simplify this into a nice whole number, we'll just leave it as it is. So again, just to talk you through it, to get the modulus of Z, we squared the real part, we squared the imaginary part. We simplify that out, and then we get our answer. Credence, maths and physics. Hi everyone, so today I'm going to talk to you about adding and subtracting complex numbers. So this is actually pretty easy to do. You have a lot of practice from it during normal algebra. Just like when we're adding x terms and normal terms, what we do is we group like terms and add them. So here our like terms is x and 2x and 3 and minus 5. So we would group those like terms together, our x's and our 2x, our 3 and our minus 5, and then we add those terms to simplify. X plus 2x will give us 3x, and 3 minus 5 will give us a minus 2. So now we've simplified that fully. Well, that's an algebra example, but with complex numbers it actually looks very similar. The only difference is instead of x's and normal numbers, we're going to have real numbers and imaginary numbers. So let's look at an example now that involves two complex numbers. So our first complex number is 5 plus 7i, and our second complex number is 2 minus 4i. So the first step in these questions is just remove the brackets. So 5 plus 7i will stay the same, and then we're going to have a 2 and a minus 4i. Now what we're going to do is combine our like terms, just like the algebra example we looked at before. So we're going to combine our real numbers, 5 and 2. We're going to combine our imaginary numbers, 7i and minus 4i. Now for the sake of making things simple, we're going to just rewrite those next to each other. So the 5 plus 2 will go next to each other, and our 7i minus 4i will go next to each other. Again, real is going with real, and imaginary goes with imaginary. Now what we do is simplify the real terms. So 5 plus 2 gives us 7, and 7i minus 4i gives us 3i. At this point, we've simplified this whole thing into one complex number, so we've solved that question. So now we'll look at a second example. This example is going to focus on subtracting complex numbers. It's going to be very much the same, but there's one step that we just have to be a little bit more careful with. So I'll talk you through that now, and I'll highlight it when we go through. So the first thing we do is we remove the brackets. So we get 3 plus 5i for the first complex number. And the second one, when we're removing the brackets, we just have to remember and be careful about the fact there's a minus in front of the bracket. So what that minus does is it changes the sign of everything inside the bracket. So minus 2 is going to come from 2. And our minus 3i is going to change into plus 3i. Now again, after we've removed the brackets, the next step is the same. We're just going to group like terms. So real terms are going to be grouped together, and our imaginary terms are also going to be grouped together. So this will give us 3 minus 2 plus 5i plus 3i. So 3 take away 2 will just give us 1, and 5i plus 3i will give us 8i. So now we've simplified this to being one complex number, so at this point we know that we have solved the question. Now you don't necessarily need to underline these in different colours the whole time you're doing it. I'm just doing it to help you visualize what I'm doing as I go from each step to the next. So you can do it if you like, but do not feel obliged to.